Hello everyone. We are going to begin the chapter Particle-like Properties of EM Radiations from Quantum Mechanics. So as the title of the chapter itself says, here we are going to discuss the particle nature of EM radiation. And we all know that EM radiations are waves, and of those waves the particle nature is going to be discussed. In classical physics, particles and waves were treated as separate components. Also, classical physics failed to explain the phenomena at atomic level, and it was unable to explain the hydrogen spectrum, stability of atom, blackbody radiation, photoelectric effect, and many such phenomena. But coming to quantum mechanics, with the dual nature of matter, we see the wave nature as well as particle nature of matter. And this was discovered and verified with various experimental evidences. So here we are going to analyze first the particle nature of EM radiations, that is the particle nature of waves. So as we know, EM radiation is clearly a wave, that is electromagnetic wave, and definitely therefore it is having its wave nature.
In the beginning of this chapter, we are going to mention the basic idea of EM waves and the associated characteristics. EM wave can be described as coupled electric and magnetic oscillations that travel with the speed of light. We have learned that a point charge produces an electric field, and at a distance r from the point charge, the field produced can be expressed as E is equal to 1 by 4 pi epsilon naught q by r square into r cap. And a straight current carrying wire produces a magnetic field, and at a distance r from the current carrying wire, the field produced is B is equal to mu naught I by 2 pi r phi cap. Now, when there is an accelerated charge or time varying current, we obtain an electromagnetic wave produced from such a source. And in an electromagnetic wave, there are both electric field component as well as magnetic field component. And this electromagnetic wave varies with both position and time. Let us consider a plane electromagnetic wave that is traveling in z-axis direction, and we can describe such a wave with the expressions E is equal to E naught sine kz minus omega t I cap and B is equal to B naught sine kz minus omega t j cap, where k is the wave number that is associated with wavelength of the wave, and omega is the angular frequency which is associated with its frequency. We can relate the wave number and wavelength with the expression k is equal to 2 pi by lambda and omega is equal to 2 pi f. So here we can see that the direction of electric field component is in I cap direction, which is in the x-axis direction, and the magnetic field component is in the j cap direction, which is in the y-axis direction. And the direction of propagation of the wave is in the z-axis. So it is clear that in an electromagnetic wave, the electric field component and magnetic field component are perpendicular to each other, and these both are perpendicular to the direction of propagation of the wave. So this is how we represent an electromagnetic wave in general, and we know a well-known expression that relates the wavelength and frequency of a wave as lambda f is equal to c. And now, taking lambda in terms of wave number and f in terms of angular frequency, we can obtain the relation as omega by k is equal to c. That is, the ratio of angular frequency to the wave number is the speed of the electromagnetic wave. Also, we have learnt in electrodynamics that the ratio of magnitude of electric field to the magnitude of magnetic field, that is E naught by B naught, also gives the speed of our electromagnetic wave. Now, in electromagnetic wave, the energy flux of the wave is represented using a vector called the Poynting vector. Here we can see that vector S, the Poynting vector, is expressed as 1 by mu naught into E cross B. And we have already represented the electric field component and magnetic field component, and using that we obtain the expression for Poynting vector as 1 by mu naught E naught B naught sine square kz minus omega t k cap. So we can clearly see that the Poynting vector is having the direction of propagation of the wave itself. That is, the wave that we consider is having the propagation in z-axis, that is k cap, and we obtain the direction of Poynting vector to be in the same direction. The energy flux of EM wave, which is given by the Poynting vector, represents the power per unit area of our EM wave. Therefore, the total power of our EM wave can be taken as Poynting vector into its area that is perpendicular to the propagation of our wave. Therefore, the expression for power becomes 1 by mu naught E naught B naught A sin square kz minus omega t. Here we use the relation E naught by B naught equal to C, and we convert the B naught in terms of E naught, and we get the expression as P is equal to 1 by mu naught C E naught square A sin square kz minus omega t. So this is the expression for power of our electromagnetic wave. And now to get the actual power of our electromagnetic wave over a complete cycle, we take the average value of this power expression. And the average value of power over a complete cycle is obtained as total power by total time, that is 1 by t into integral 0 to t p dt. And on taking the average value, we obtain the final expression as P average is equal to 1 by 2 mu naught C E naught square A. As we know, the average value of sin square theta is half, and that results in the expression P average is equal to 1 by 2 mu naught C E naught square A. So this is the expression for power average. Now the average power per unit area is the intensity of our electromagnetic wave. Intensity I is equal to P average by area, which is obtained as 1 by 2 mu naught C E naught square. And from this expression we can see that the intensity of our electromagnetic wave is proportional to the square of the amplitude. So from all these discussions, two important inferences that we obtain that the intensity of our electromagnetic wave is proportional to the square of its amplitude that we just saw, and the unit of intensity is watt per meter square. Also, the intensity, which is the power per area, varies with frequency. But for our visible light, this fluctuation of intensity with the frequency is not visible because the frequency of light is of the range of 10 raised to 15 Hertz. That means there are 10 raised to 15 oscillations per second. This makes our eye unable to observe the fluctuation of intensity with frequency. So this is all about the general aspects of an electromagnetic wave, and here there is a representation of the electromagnetic wave where electric field, magnetic field and the direction of propagation of the wave are mutually perpendicular. As it is very clear that the electromagnetic radiations or EM waves are wave in nature, we should see the electromagnetic waves undergoing the phenomena called interference and diffraction. Interference and diffraction are exhibited by a wave, and therefore electromagnetic wave should also undergo both these phenomena. Let us first analyze about the interference. When two or more waves of same nature meet in a region, then they undergo interference and produces an interference pattern. The interference pattern consists of dark and bright fringes which are equidistant from each other. Now, if the two waves that are meeting at a point are in phase, then we get a resultant wave which is having greater amplitude and high intensity, and that produces a bright fringe at that point. This is called the constructive interference. So the condition for constructive interference is that the two waves that are meeting at a point should be in phase. Here is a representation of the constructive interference. As we can see, two waves that are in phase when interfere result in a greater amplitude and therefore in a greater intensity, producing a bright fringe. Now, if the two waves meeting at a point are out of phase, then the amplitude and intensity of the resultant wave becomes minimum or becomes zero, and thus we obtain a dark fringe at that point. This interference is called the destructive interference. Here is the representation where we can see that two waves which are out of phase, when interfere, we obtain a resultant wave that is having zero amplitude. The interference pattern of light was experimentally observed by the famous British physicist Thomas Young, and his experiment is well known as Young's double slit experiment. In his arrangement, he used two coherent sources of light which were placed at a distance d from each other, and a screen was placed at a distance capital D from the source, and two waves from these two sources S1 and S2 interfere, resulting in dark and bright fringes, and an interference pattern was obtained on the screen. Now let us consider a point on the screen where we observe the interference pattern, and let the distance from the sources S1 and S2 to the point under consideration be x1 and x2 respectively, and the distance x1 and x2 are taken in terms of the wavelength of the waves. And it was observed that the path difference x2 minus x1 was obtained as n lambda wherever we saw a constructive interference, and the path difference x2 minus x1 was obtained as n plus half lambda wherever a destructive interference occur, where n is an integer and lambda is the wavelength of the source. So the condition based on the path difference for obtaining constructive and destructive interference is that path difference should be n lambda for constructive interference and path difference should be n plus half lambda for destructive interference. Now by analyzing the experimental setup further, we can obtain the distance at which we obtain a constructive interference and destructive interference from the center of the screen. So let us consider a point on the screen which is yn distance away from the center of the screen, and the distance between the sources S1 and S2 is taken as small d, whereas the screen is kept at a distance of capital D from the source. Now from the figure we are having two right angle triangles, and we can easily obtain the expressions for x2 square and x1 square by applying the Pythagoras theorem. x2 square is obtained as d square plus d by 2 plus yn the whole square, and x1 square is obtained as d square plus d by 2 minus yn the whole square. Now by subtracting these two equations and solving, we obtain finally the expression for yn as yn is equal to capital D x2 minus x1 divided by small d, where x2 minus x1 is the path difference, and we have already seen that the path difference is having certain condition to obtain constructive and destructive interferences. Now by using the results of path difference for constructive and destructive interferences, we obtain the expression for yn to be n lambda capital D by small d for constructive interference and yn as n plus half lambda capital D by small d for destructive interference. Thus we obtain the expression for distance at which we get maxima and minima, that is bright fringes or dark fringes, from the center of the screen. A similar kind of interference pattern is observed on the screen due to the interference of EM wave, in which we see the dark and bright fringes which are equidistant from each other. So this is how electromagnetic waves undergoes interference and we obtain interference pattern.